A2 Maths, normal distribution. Right, so what we're going to do is we're going to start off with a bit of GCSE histogram work with you first of all. So 200 people measuring the weights of their dogs. They put it into the histogram you can see in front of you. And all I'd like you to do is see if you can work out the probability that a person that had a dog weigh in between 30 kilograms and 55 kilograms is selected out of all of those people. Okay, so you want to pause it, have a go at calculating the answer to that question first of all. And then when you're ready, you can just restart. Okay, so the way you're going to work out between 30 and 55 is working out the total frequency. Okay, because if you can work out the total frequency of dogs that are between 30 and 55, then you can work it out as a percentage quite easily out of the 200. So the way you work out the probability or the amount is by working out the area underneath. So there's 36 people there, 40 there. If you've forgotten how these are worked out, it's the distance across times by the frequency density. So there's a bit of guesswork on your part. 10 times roughly 3.6, 46. So if you've got those slightly off, it doesn't matter. And then what? 139 people then had dogs weighing between 30 and 55. You may have a slightly different answer to that, but it shouldn't be far off. So the probability is going to be that, 139 out of 200. So a probability of about 70%, roughly 70% is the probability of getting a dog between 30 and 55. So all of that is GCSE work, but it's important to start to understand that the area under the curve represents a probability. Okay, so what I'd like you to do is on a whiteboard or on a piece of paper, I'd like you just to have a think about this. Got a random sample of the heights of 1,000 men. We know that the average height of a man is 1.75 meters. The class widths are separated out in 10 centimeters equally from 1.5 to 2 meters. So 1.5 to 1.6, 1.7, 1.8 up to 2 meters. What I'd like you to do is just sketch down roughly what you think the histogram is going to look like if you took 1,000 men. Okay, that's a lot of people. Okay, so hopefully, once you put them around here, you would recognise that most of the men would fall into this 1.7 to 1.8 region. That's going to be the biggest bar by far. It's got the average in the middle, and most people wouldn't deviate too far from that person. But then once you go past either 1.8 or 1 point below 1.7, you still get quite a lot of men that fall into that region. Okay, but nowhere near as much as the middle section. And then you also, after that, you're going to get some people that are very tall and some people that are quite small. And they're going to be in these two bottom regions out of those days of men. And then, of course, there would still be some that would go below that and above that. Okay, but most people would lay in this middle region. Right, very good. Just put that to one side or rub it out. Have a go at the same sort of thing again, but this time, what would it look like if it was 5 centimeters? So 1.5 to 1.55 to 1.6, 1.65, and so on. Okay, so just have a think what that would look like. Okay, so again, same sort of thing as before, isn't it? That you'd get most of the people lie in the middle. All right, there's the middle, 1.5, so most of the people would lie between there, probably roughly equally spaced. And this is where the mistakes often come in. Because what you often get is you get people that come straight down like that. Sometimes they swoop down like this. But what's going to happen is, although most people lie in that middle region, there's still quite a few people that will still lie on either side of it. So the 1.8 to 1.85 and the 1.65 to 1.7 is still very big. Okay, but then once it starts to go down, it starts to go down quite quickly. But then once it gets down to this sort of level, there's always going to be a few others. It doesn't just cut straight down at that same pattern to 0. Okay, and it certainly doesn't do that sort of pattern or like that. It sort of comes down gradually. Okay, last one then. I don't want you to plot the scatter graph this time. What I'd like you to do is just draw the top of what the histogram would look like if it was 1 centimetre. So I certainly don't expect you to do bars for 1.5 to 1.51 and so on. But what sort of shape, once you draw that histogram, once we draw those individual bars, what sort of shape are you going to get? Okay, so you know most of it's in the middle. It's more thinking about what's going to happen on either side of it, and on this side, what's the shape going to look like? Okay, so pause until you're ready. Okay, so what you should have found is this, that the bars should be in that sort of pattern. Most of them in the middle, but as they progressively go up from there, they do go down, but they never go to zero. They just sort of tail off a bit like that. And the same on this side. Now the shape you get is what's called a bell-shaped curve. That sort of curve that you can see in front of you, that sort of bell-shaped curve, is what we call a normal distribution. What I'd like you to do is grab your notebooks then. Now, some continuous random variables, this is what we mean by a continuous random variable, because to measure, let's take for example the previous example where we measured height. If you're measuring height, because you're measuring it, therefore it is a continuous data set. All right? Measuring is a continuous data set, so therefore that is a continuous random variable. Okay, as opposed to if you're counting something, you've done binomial distribution already. A binomial was looking at counting successes, and that was a discrete random variable. So this is slightly different. This is a continuous random variable. So a continuous random variable can be modelled using a normal distribution. And a normal distribution is a graph of a population that is normally distributed, is what's called a bell-shaped curve. It looks like this. It always has the mean in the middle. So the population mean, whatever the mean population is, and it goes out symmetrical from there. So most people lie around that middle, that top end, and then progressively go out and decrease down there, and the same on this side. About 50% lies on the other side. That makes sense because it's symmetrical. So there's always 50% of the population that's bigger than the mean and 50% of the population that is smaller than the mean. And a population mean in the normal distribution is exactly the same value for the median and also the mode. So the normal distribution, if you want to work out the mean, median or mode, they're always exactly the same value. Okay, that's an important hint for that exam, because sometimes you might get a quick 1 mark question on this, maybe towards the end, that says what's the median of this normal distribution, and you recognise that it's exactly the same as the mean. It's not always the case. This is the reason why we started with histograms. We started by comparing to histograms. Histograms are discrete in the sense that you're putting the heights within discrete sections, but just like histograms, the area underneath the curve is about probability. Exactly the same with normal distribution curves. Okay, so the spread of the population is measured by what we call the standard deviation. How far things deviate from this mean is what we call the standard deviation. Now, whenever you've got a normal distribution, it deviates out by only about 3 deviations, but we'll come back to that in a second. When you write the normal distribution, you write it like this. X is distributed normally, so it follows a normal distribution, with a mean mu, so whatever the mean is, and a standard deviation squared. Now, standard deviation squared, as you've seen previously, is what's called the variance. So the standard deviation might be this symbol just here, what's called sigma, but the variance is sigma squared. So it's important to remember that when you come to writing down your distribution, like you're used to with with binomial distribution, when you write it down for normal, it's always the mean and the variance. Okay, for binomial, it's the number of trials and the probability of success. It's different for different distributions, so just be aware of that. So a random variable x is distributed normally with a mean mu and a variance sigma squared, like I just said. But just pause until you got your notes down. Okay. So the approximately 68% of the population. So it doesn't matter which population you're looking at. That could be, for example, it could be the heights of men that we saw earlier on. It could be sentence length in a book. It could be the weight of pigs. It could be absolutely anything. If it follows a normal distribution, then when you work out one standard deviation from the mean, you always have roughly 70% of the population lies within one standard deviation. So one standard deviation is about there and there, and about 68% lie within that region. So if you know what the standard deviation is, and you can add it and take it away from your mean to get you these two boundary points, then you know that roughly in the middle of that is about 68%. Okay? By the time you get to two standard deviations, you've covered nearly 95% of the population. So let's say the standard deviation is just 2, just the number 2. Then you got mu plus 2 there, mu plus 4 is there. Opposite side will be take away 2, take away 4, and about 95% of the population will lie within that region. Okay. By the time you get to 3 standard deviations, you've pretty much got everything. It's very rare that something deviates more than 3 of your standard deviations away from your mean. So if you've calculated what the standard deviation is, so for example, a minute ago I said, let's say the standard deviation is 2, okay, then that means that by the time you get to 2, 4, 6 standard deviations, it's very unlikely that somebody will measure 7 standard deviations or 8 standard deviations and so on away from that mean. That covers nearly 100%, 99.7% of the population is within 3 standard deviations from the mean. Okay, right, so what I'd like you to do is, again, just grabbing a piece of paper or doing it on your whiteboard, however you want to do it. We've got a normal distribution. The mean is 15. Okay, so your average is 15. That could be 15 meters, it could be 15 kilometers, it could be 15 grams, it could be 15 seconds. It's anything that's been measured. Okay, so 15. The variance is 9. So the variance is 9. Beware, that is the variance. And what I'd like you to do is just show me what the graph would look like. So a quick sketch of your bell-shaped curve. What would the numbers on the bottom look like? Okay, so I'll pause there, have a quick go. Okay, so let's see how far you got then. So you've got your nice bell-shaped curve. Get used to sketching them. You sketch them a lot. So you've got this nice bell-shaped curve. The mid value, the mean, mode, and median, right, the mean is 15. You can definitely put that on straight away. There we go. Now it separates out from that in roughly 3 standard deviations. By the time you get to about here, that's 3 standard deviations. So what I would recommend you do is just take 3 steps out, 1, 2, 3, and mark down 3 separate markings. Same with this side, 1, 2, 3. Roughly 3 standard deviations on each side. The standard deviations are the square root of 9. That is standard deviation squared there. So be very careful. That's why it's 3. Okay, don't make the mistake of putting 9, 18, 27. It's not. It's 3, 6, 9. Right, but it's no good just putting 3, 6, 9. There's 15. What would a standard deviation away from there be? It'd be 15 plus an extra 3. So you get 18. From there, plus another 3 would get you 21. Plus another 3 would get you 24. It's highly unlikely, if you had an average of 15 and a variance of 9, that you would get a result that was bigger than 24. So let's put it into context. If this was, let's say, the weight of some type of creature, and it was 15 grams, and you went out into a field and started weighing all these different creatures, it's very, very unlikely that you would get any creature that weighs more than 24. Most of the creatures would lay between 18 and 12, which is still going down. 12, 9, 6. About 68% of those creatures would weigh between 12 grams and 18 grams. About 95% of all the creatures you found would weigh between 9 and 21. And nearly 99.7, nearly the whole population, will be between 6 and 24. It'd be very unlikely to get anything that goes more than that or anything that goes smaller. Okay, so try again. A bit quicker this time. Pause it, have a go at those, see what you get. Okay, so I've got mean of 1.9, smack bang in the middle. 0.04 square rooted, 0.2. So you're going to go out by 0.2 on this side. 1, 2, 3 standard deviations. Same on this side, 19, take away 0.2, take away 0.2, take away 0.2, 3 standard deviations on that side. So that's exactly what your graph would look like, and then you can start to do some work on your probabilities after that. So try again. 27, mean of 100. See what you get. Have a think whether you're right or wrong. If it's incorrect. So we've got that. 27. 27 smack bang in the middle. Mean is 100, so 37, 47, 57. When you go down, 17, 7, minus 3. Now, depending on the context of the question, this would show that it's probably not normally distributed. Because let's say, for example, this was scoring a test, or it was time running a race, or something like that. If it was that sort of situation, then you could say, I don't think it's normally distributed because you shouldn't be able to go down to minus 3. And I would agree with you. Sometimes you get those types of questions saying, why do you think normal distribution is not appropriate? Because it goes down to minus 3. But don't forget, it could be temperature. Now, if it's temperature, or it could be some sort of costing exercise or something like that, where minus 3 does make sense. A temperature of minus 3 is perfectly reasonable if that could be like an average fridge temperature or something. Room temperature. Okay. What I'd like you to do then is, without really giving you too many hints, you know about the rough estimations of the 68, the 95 and the 99.7. I would like you to just take those a little bit further and see whether you can answer these probability questions. Okay, so there's graph. You know it's 10, you know it's 4, so sketch out the bottom parts and then just see if you can think about the probabilities of these things just here. Okay, I'll pause. You pause your screen, have a go at those 6 questions, and we'll look for the answers. Okay, so what's the probability x is less than 10? So hopefully you've realised that 10 is smack bang in the middle. Because it's normally distributed, probability of getting less than 10 is going to be everything below that. So we can put down 50%. That's definitely the answer to the first one. What's the probability of getting less than 10? 50%. Okay, number 2. What's the probability of getting between 10 and 12? So I've put the answers down the bottom because my variance is 4, so it's 12, 14, 16, and so on the other side. So what's the probability of getting just this region just here? Okay, well, we know that between those two standard deviations just there is roughly 68%. So because that's 68%, half of that, because it's symmetrical, is going to be 34%. So you can use the facts that you already know to calculate some of these. Now, if that's enough information to help with the others, by all means pause and carry on with those. Okay, right, 8 to 14. So that's from there to there. We can see that all of this is 48, is 68 already. So what's the difference between 8 and 14? Well, everything up to 14 is 95%. Okay, we know that the middle section is 68%. So I know that these two bits just here must be the difference between 95 and 68 shared by 2. So that means that that one there is going to be 13.5 because both of them put together is going to get you 27, which is the difference between those. Right, which ones do I want then? Well, I want everything from 8 up to 14, so 68 and it's 13.5, so I'm going to be getting 81.5. Okay, what about the probability of less than 16? Well, I know between 4 and 16 is 99.7. That means that these two sections at the end, anything below 4, anything above 16, sorry, should be that 0.3%. So that means that each of those is going to be worth 0.15. So what's the probability of less than 16? Well, it's all of the 99.7 plus this extra 0.15. So that's going to be 99.85. Okay. Right, what about 4 and 8? So that's there to there. How would you work out that probability between those two? So I know that the whole lot is 99.7. I know that the middle section is 68. I can look at the difference between those two. And that would tell me that this is worth 15.85 and that's worth 15.85. And what do I want? Well, in fact, I just want that section, don't I? I want the 15.85. There we go. I can put that on. Okay. Then the last question is It's quite interesting. What's the probability of getting exactly 8? So the probability of getting exactly 8, just there, is going to be the area under just 8. Now 8 does not have a thickness. So because it doesn't have a thickness, what you're going to do is you're going to end up timesing by 0. And anything times by 0 is always going to be 0. Alright, so there's no width, therefore no area, therefore the probability of getting a single value is always going to equal 0. Now that means that it's exactly the same answer if I had the probability of less than 10 or less than or equal to 10. It makes no difference if you have a less than or equal to in it. No difference at all. And the same with any of these, which might be greater than as well. Okay. It's also quite interesting that although we've all passed the 1 meter mark in our heights, the probability of finding someone in the world that is 1 meter tall exactly is still 0%, because it's not, because you cannot find something of an exact value. It just doesn't work. Okay. So the problem is it's all well and good if they hit those exact values for the 1 standard deviation, 2 standard deviations, or 3 standard deviations. But what happens if it's not one of those exact values? What happens if it's a different value? So luckily, our calculators can do all the work for us. So we won't need to do all the bits we just did. We can do it on our calculator. So what I do is grab your calculators. Make sure you've got the calculator in front of you, and you're looking for the normal CD function on the distribution menu. So the first menu, it should say distributions. So you can click on that, and then you're looking for the normal CD function on your calculator. Right. When it comes to the distribution, you're asked 2 questions. You've got the mean and you've got the standard deviation. So depending on the question, you need to put those 2 pieces of data in. Just make sure that you are putting in the standard deviation if you're asking for it, or the variance if it's asking for it. Right. You also asked a lower bound and an upper bound. So if you're looking for between 2 numbers, okay, A and B, then the lower bound is the one that's the smaller out of the 2, and B is the upper bound. Now you might have it so it's both above the mean. That's okay, but A is always the smaller out of the 2. If you're looking for just below something, then what you want to do is your lower bound that's been asked on your calculator, so where it says lower bound, just put a very large negative number. So minus 99999 will do fine. That way, this value is so far over here that it doesn't make any difference to your calculations. And the same the other way around. If you ask for a greater than, your upper bound could be something massive like 9.999. So, sorry, 9,999, something like that. Okay? And that way, although you're still doing one of these types of questions, either part of it is made redundant because you put in some very big values. Okay? Right, that way it can ask any question. You could be asking a question between 2 values, you could be asked a question which is less than a certain number, a question that's greater than a certain number, and as long as you put in your mean and standard deviation, your calculator will do all the work for you. It will do all that calculation. Okay? What I'd like you to do is just have a go at just checking those ones that you just did. You got the answers that you knew, so just see what the answers your calculators actually did. The only interesting one on that is number 6 that you can't really put in. You could try putting 8 in for both values and see what it says. Okay, so pause, have a go yourselves, just confirm you can use your calculators, and then when you're happy, we can move on. Okay then, so what I'd like you to do is on page 400, just have a go at exercise 1.1. So they involve you just using your calculator skills, making sure you're putting in the correct values for the mean and the standard deviations and the variance, whichever one is asking for, and also practicing some of those boundary questions. Okay, so all right, so grab a piece of paper, grab a whiteboard, however you want to do it, and what I'd like you to do is show me, or have a go at sketching yourselves, what that looks like. Okay, so on a normal distribution, the probability of getting below a certain value is 25%. So how would you show that on a normal distribution graph? Right, so hopefully you thought, right, here we go, I've got the graph drawn. Below a certain value, well, below mu there is going to be 50%, all of that section just there. That's below 50%. So below this section is 25. So it's going to be a bit further down. It's probably going to be somewhere in this sort of region. If that's 50%, it's probably going to be somewhere about there, isn't it? Because you're going to be shading it in. So you're actually shading about 25% just there. It's very easy to think it's down here, but actually all of that area does equal all of that bit. Mine is accurate. Okay, even if it doesn't look quite right, it is accurate. Okay, try that one then. Probability of greatest number is 40%. Greater than or equal to. Interesting. Okay. Pause if you need to. Let's see what you got then. So there's my 50%. Greater than that is 50%. So that's all this section. Greater than or equal to makes no difference. Don't be fooled by that equals to. It's still the same. It's still a straight line. Straight line at A, 40%, and just a small 10% mark just there. Okay. So 40% looks like that. Okay. What else could you do to derive that A value? So you know that the probability of greater than A is 40%. How else could you rewrite that and still get an answer on this graph just here? Okay, using that A value. How else could you do it? Okay, well, if you said greater than A is 40%, but another way of saying it is the probability of less than A is 60%, you'd be correct. It doesn't matter about this sign. It doesn't matter if you said less than or equal to, all right, because it can't equal. The equaling the value is equal to 0. But sometimes it's important to make sure that you're aware that you can flip it round. It will help later on when you use your calculators. Okay, all right, try this one then. Greater than A is 60%. That's a little bit more interesting. Okay, so greater than A is 60%. So it's going to be that. There's 50%. Greater than A. We know it's greater than, so it's shaded on that side. 60% means it has to be the 50% and more. Okay, how else could you ask that question? Okay, how else could you derive that A value? And yes, you're right. Less than or equal to A is 40%. They're exactly the same A value, just there. Okay, so less than or equal to A is 95%. So how would you show that on your graph? How would you shade that area? Okay, so how would I show it? I would have about that much region. Doesn't look it, but it is, again, it is accurate. That's about 5%, about 1 in 20 just there. Would be in that region. So in this one, how would you define this? Exactly what I just said. Greater than A is about 5%, about 1 in 20. Right, try that one then. That one's a little bit tougher. Shade the area that represents between 80 and A equals 20%, given that your distribution looks like that, your normal distribution. Okay, so pause if you need to. I've put 80 in the middle. I know it goes out 25, so that's the sections of 5. So I know that 20% is going to be roughly in that region. It is greater than 80%, but it's less than A, which is there, and that's where you get the 20% from. Try this one. We know that it's still got the same distribution, so hopefully you've got the same graph. So there's my 80, 70 is about there. It's going out in 5s, so that's at 80, 75, 70 is there. Okay. I know that that is going to be less than 50% because all of that up to there is 50%. So I know that 65% is going to be over here somewhere. So I can definitely put that in. There we go. Right up to about there, 65%. Right, so the reason why you've done those is because they're backwards questions to what you had before. If you're given a probability, you need to find the value that will get you that probability. Okay, so the question you practiced before is you were given a value, what's the probability? The inverse normal function on your calculator does the opposite. You put in a probability and it will tell you the value compared to your mean. So grab your calculators, make sure you got to the distribution menu and you're looking for this inverse normal button. Same as before, you've got your mean, you've got your standard deviation in your distribution. So you make sure you put both of those in, being very wary not to put variance in by mistake. Now, if the probability is less than A, equals P. A is the upper bound and P is your probability, your area shaded. Okay, so you're looking at putting the A value in and putting in the P value. Sometimes it's a greater than. All right, so if the question is a greater than and your calculator can't do that because your calculator only does less thans, then what you need to do is you need to look at probability of less than A. Now the probability of less than A is always 1 minus the probability. So if probability is, let's say, 10%, 1 minus P would be your 90%. If that's 0.2, that would be 0.8. Okay, now that matters because your calculators can only do these types of things. If your calculator wants, or sorry, if your question asks you to work out between two values, your calculator can't do that again. So what can you do? If you only need to write it in this sort of format, is you can work out everything up to B. Okay, everything up to B. Now that would give you everything, but it also give you things you don't want, like this bit. So what you can do is you could take away everything up to A. It's exactly the same as how you've done integration. You do the big value, take away the small value. Okay, and that's exactly what you do here. You work out the bigger value of getting below that using your calculator and take away the probability of getting below the A because that's the bit you don't want. All right, so you can make sure you can change these questions, these probability questions, so they're always less than. And you can put in the A value or the P value dependent then. Okay, so that's a quick check on how to use your calculator. Right, so let's go back to this question just here. So I asked you to shade that area. You've got a visual idea, you knew what to do, you knew it was about there. So what is this A value to make that 20%? If I know that my mean is 80, my standard deviation goes out in fives, so it's 80, 85, 90, 95, 75, 70, 65. But what would this A value here have to be so that I know it's exactly 25%? So I grab my calculator, I put in my mean, I put in my standard deviation of 5, I put in my p-value of 0.25, not 25, be careful, and that should tell me what my A value is. It should tell you the A value is about 76.6. Don't just go with it, make sure you look and you say, yeah, I'm happy with that, because I know that's 80, I know that's going to be 75 just there, so 76.6 makes sense to me, sounds correct. Okay, so try this one. Given that normal is 50, standard deviation is going to be 3 because it's a variance of 9. Greater than A is 40%. This is the one we drew. We managed to draw that. I know it's very close to the 50. It's just a bit above it. Your calculator can't do greater thans. So the first job you've got to do is change it into 60%. So we can do the probability of less than A is 60%. And then once you've done that, your calculator should tell you it's about 50.8, which again should make sense from the sketch, and it should make sense to you. Always think about the sketch, think about where the values are, because then your calculator won't just give you an answer that's completely out there. Okay, try this one. Given that X is distributed normally with a mean of 10, so that's in the middle, and a standard deviation and a variance of 1, both of them are worth 1, then we're getting a probability of greater than A is 60%. So what do I get? There's 10, jumps up in ones, so it's 11, 12, 13. On the other side, it would be 9, 8, 7. Greater than 60 is this region, so less than this region will be 40, and that's the one we're looking for on our calculators. So a value of about 9.75 to me would make sense because that's 10 and that's 9. So 9.75 seems about correct. Okay, try this one. 1436, standard deviation of 6, 95. Try it then, see what you get. Okay, so hopefully put 14 in the middle. 95% is going to be all of that 50% plus this all the bit, so quite a lot of it. There's my A value. Get my calculator, 23.9. Should make sense because that's 14 plus an extra 6 would be 20. That's 26, so it's about right. And don't forget, you can also put that back in your calculator backwards to check you get the 95% out as well. Okay, so this is a bit more interesting. It's between 11 and 8 is 20%. So I know that I'm looking for this value up to A is 20%. So how would I type that in my calculator? Well, you can do everything up to A, okay, take away everything below 11, but you know that everything below 11 is 50%. So the easiest thing you could type on your calculator here is the 50% plus the 20%, which is 70%, and that would tell you the A. So what's the probability Y is below A would equal 70%. That will tell you about 13.1. So just thinking about the graph, thinking about how you could use the graph to help you solve the problem. What about this one? Between 40 and something else equals 65. So I've got this situation just here. 40 is not so helpful. Okay, so I might need to work out what the probability of below 40 is first. I know it's going to be 65. So there's 40. Some A value is going to be over here to get you 65. Okay, right, so how can that help me then? Well, I can get my calculator to work out what's the probability of getting below 40. So that's like a previous question. If I know what the probability of getting less than 40 is, then I could definitely work out what the probability of less than A is, because it's those two things put together. Okay? Right, grab your notebooks then, please. And in your notebooks, we're just going to look at one last thing before I give you some questions to do, called the standard normal distribution Z. So the standardized normal distribution Z has a mean of 0 and a standard deviation of 1. Now this is absolutely vital to understand this part in case you get questions that you don't have the mean or you don't have the standard deviation. If you don't have the mean or the standard deviation and you need to calculate it from certain information, you have to understand about the standard normal distribution. Okay. So do a quick sketch. It's got a mean of 0. It's got a standard deviation of 1. It's also got a variance of 1. Doesn't really matter which one you use. And you'll notice that the letter on the front has changed to Z. Whenever you use Z, it's always about this. It's always a standard normal distribution. And we also get what's called a Z-score. A Z-score is the measure of how many standard deviations a value is to the right or the left of the population. So if it's positive, you know it's 1 standard deviation, 2 standard deviation, or 3 standard deviations from your mean value. If it's down the bottom, if it's below, you might be able to say, look, it's 2 standard deviations below the mean. It doesn't matter what the mean or the standard deviations are. You can say with a Z-score of how many of those standard deviations there is below the mean. Okay, that's why it's quite helpful. Having these two numbers, 0 and 1, means you can talk in terms of how many standard deviations above and below the mean is. To formulate the Z-score, it's always the X, which is your value, whatever it is. Okay, so that could be your number. Let's say it's number 6. Your mean could be 5, and your standard deviations could be 0.2, and you could calculate a Z-score based on that information. Your mean of your value of 6, take away the mean of 5 divided by 0.2 would get you a Z-score. It would tell you how far away your value of 6 was in comparison to the mean of a 5. Okay, you might go, oh, it's just 1, but that depends on the standard deviation. So when you divide by the standard deviation, you will get your Z-score. And your Z-score tells you how many standard deviations it is. Okay, so we'll look at an example of one of those. If you need more time, pause it. By doing exercises 1.4 and 1.5. One of those is just purely about Z-scores and working out a Z-score. And the other one is practicing some of the skills we just did with probabilities. Okay, so have a go at both of those exercises before we move on. Okay, so a question for your notebooks then. So grab your notebooks out. Given that we have a distribution, X, which is normally distributed, with an unknown mean. We don't know what the mean of the population is. We do know the standard deviation though, and the variance is 16. So we know the standard deviation is obviously 4. And we've also got another bit of information as well. we know the probability that getting above 20 is equal to 76%. Okay, so someone's come along and said, well, to get above 20, about 76% of the population get above 20. From that, we need to calculate the mean. Okay, so knowing that one bit of information, that get scoring above 20, having a weight above 20, whatever it is 76%, we should be able to calculate the mean. Okay, right, stick with your notes then, let's do a model solution. So the first thing we want to do is just sketch out a quick normal distribution curve and just get a rough idea of where greater than 0.76 is. It's important to have that idea in our heads. It doesn't need to be a work of art. Okay, I know mine's accurate, but yours doesn't have to be. And just to have an idea that if we want above a value is 76%, whereabouts will that lie? We know it's greater than, so it's going to be shaded on this side. We know it's going to be before that because that's 50% there, so it's roughly over in this region. That's all we have to have in our head. It doesn't matter where it is, it doesn't matter if you got it in the wrong regions here, as long as you've got some sort of idea of whereabouts it is. Okay, right, we can use our calculator. Okay, calculator to find out the z-score. Okay, from this. What is the probability of getting 0.76? If that is our shaded region, we would have to type in our calculator the opposite to that. We'll be using 24 in our calculator. That's what this is saying. And to find the z-score. So we can put our probability of 0.24 and the z-score comes out to be minus 0.706. This 20 is about 0.706 standard deviations below the mean. Notice on our calculator, we are putting in these values, the standard curve. Nothing to do with the 16. That's a mistake people make. They think they put the 16, they don't. You are sticking with a standardized curve because you're trying to get a z-score. Now, once we've got that z-score, now we can use the z-score formula. The z-score formula, that's what I just mentioned. The z-score formula looks like that. There we go. It's x minus mu divided by the standard deviation. We've got the standard deviation. We've got the z-score. We've got an x value because it was the 20 that we used to get that. And we don't know what the mean is. But we can put everything else in. So put it all into that equation. Bit of rearranging. Pause there, just number crunch, see if you can figure out your mean. And then your mean is 22.8. Does that make sense with greater than 2076? So if 20 is in the middle, does 22.8 make sense? Okay, so just have a quick go at these two exercises here. Some of them might be looking at missing out the mean. So you might have questions where they're missing out the mean or they don't know what the mean is and you have to calculate it. And some might be where they're missing out the standard deviation. They both involve the same skills. If you're missing the mean or the standard deviation, you're going to have to work out the z-score first and then use the z-score formula to find the missing mean and the standard deviation. Okay, so what we're going to look at is another question for your notebook. So we'll get that down. And hopefully you're realising very quickly when you're writing it down that this one's a little bit harder than previous ones because you haven't got a mean and you haven't got a standard deviation. What you do have is two pieces of data. So just while you're writing it down, then we'll talk about it. Okay, so pause it if you want to. So the two pieces of data we definitely got is we know that below 50 is 65%, but below 54 is 96%. So those two pieces of data are the only two pieces of data we got. And from those, hopefully, we can find out the mean and we can find out the standard deviation. Okay, so let's have a quick look at this answer in our notebooks. So the first thing I'm going to do, same as I said before, quick sketch using the normal distribution curve. So we know below a value is 65%, so it's going to be over here somewhere. And below this one is 96%. So these are the two I've roughly got in my head. Okay, so I've got an idea of what's going on. Again, that's always vitally important. They're both less thans, which has made life a lot easier for my calculator. Because what I can do is I can substitute in the 65, the 0, the 1 for the mean and the standard deviation, and the 0.96. And that's going to give me two z-scores. Z-score for this one is 0.3853, and then the z-score for that one of 1.7507. Now that I've got my z-scores, what I can do is I can work backwards, but I still don't know what the mean or the standard deviation is. So when I start using the formula, I know the Z, I know the X in that case, it's going to be 50, but I don't know what the mean is and I don't know what the standard deviation is. So I'm stuck there. Same on this one, okay? I'm stuck with the formula, but I can substitute in the 54, I can substitute in the Z-score, and end up with these two equations. Now I hope you're looking at it and thinking, well, you've got two equations, you've got two unknowns, so we can solve them simultaneously. And you'll be right. You can take your two equations, a little bit of rearranging just to neaten them up slightly. So I can rewrite that one like that by multiplying by sigma. And I can rewrite that one by multiplying by sigma. And the easiest option is just doing one take away the other. It will cancel out your means, allow you to calculate your sigmas, and then once you've got your sigmas, you can calculate your means afterwards. Okay, so that one, take away this one would work fine, wouldn't it? 54 take away 50 gets you 4, minus mu plus mu going to cancel out, and then you've got 1.7507 take away 0.3853. However you want to do it, your sigma should have got out to be 2.93. Once you've got your sigma value, you can calculate your mean, therefore 48.9. So these are the sort of top end questions where you have to figure out the mean and the standard deviation and potentially the variance. Okay, so have a quick go at those questions. Some of those get a bit tough, so don't just skip them. Do have a look at them and look at the harder question parts on them as well. Okay, when you're ready, you can move on. Okay, so this is the top end of the normal distribution work. And the examiner needs you to have some sort of understanding of points of inflection, not interflection, the points of inflection on the normal distribution curve. Also wants you to have some sort of understanding of the formula, but it's highly unlikely he's going to give you this work you're about to see to do yourself. Okay, so what we're going to look at is the equation of the normal distribution curve. So the equation of the normal distribution curve looks like that. Okay, so that formula just there would produce this lovely bell-shaped curve you see here. Not the most pleasant of formulas. You're certainly not expected to know it. You're not expected to use it. Okay. In fact, in a lot of ways, on its own, it's a bit pointless because all it does is find points on the normal distribution curve. It doesn't help you much at all. Okay. But what the examiner might expect you to do is do some sort of calculus with it. It might expect you to do some differentiation. Okay. If he does, then you're talking at the very top end. We're talking about sort of A-star work here. So we're going to actually have a go at finding the points of inflection is where the convex part of the curve, which is there, okay, which is curving like that, changes into the concave curve, which is there. That's like a cave section. So that's your concave. Here, where it's coming underneath, is going to convex. So somewhere in this region here, it changes from a concave to a convex. Okay, so a convex to a concave. And what we need to do is figure out where that point is. And that's what's called the point of inflection. So a point of inflection can be found by finding the second derivative. The second derivative can help us find the point of inflection. So a point of inflection implies that the second derivative equals 0. Okay, but as you've seen from your teachers, it doesn't work the other way around. This implies sign is correct, only pointing that direction. Okay, so this is where some of the calculus gets a bit messy. So you just got to, it's not in your notebooks, you'll notice that. Okay, because I don't want you to write it down. I'd rather you just try to get some of it in. If the examiner is going to ask you this in the exam, it'll be most likely sort of here's 3 steps, can you spot an error, that type of thing. So we're going to differentiate it. We differentiate in terms of x, and we could do that because we can ignore the mu, the sigma, the pi. They're just constant. They're just like numbers. So that's like a number on the front. These are all numbers on the inside. So when we differentiate it, what we're doing is we're just differentiating that inside bit. Okay, and that's what we've got to start with. So we're differentiating this middle section just here. How do you differentiate an exponential? We use the chain rule. Okay, so if I use the chain rule, what I'm going to end up with is the differentiation of this bit, okay, which means I bring the 2 to the front. I can get -2 on the front. The x minus the mu and the 2 sigma squared just comes to the front there. The power of the exponential stays exactly the same, doesn't change. Okay, that's the first differentiation. I'm going to do that again once I've simplified it, so I can pull that out. -2 can come out, cancels with that 2 underneath. The minus can come out there. The x minus mu can stay on the top there. And the sigma squared, and that sigma there goes to sigma cubed. And then I can go again. Now this time I'm going to differentiate. It's a bit more messy because I'm differentiating. I can ignore that number at the front, but I'm differentiating all this. It's not just a chain rule now because I've got this part out the front as well. Okay, so let's have a look what that looks like. So I'm going to use the product rule, differentiate that, leave that alone, differentiate that, leave that alone, and end up with this. So if I differentiate that, I get just 1 because the minus mu doesn't make any difference. Leave that bit alone, gets me that. Then if I differentiate this, I do the same as what I just did. So that's why I've got this same answer coming out the front with the chain rule. Leave that bit alone. That's why it's squared now, unlike last time. Once I've done that, I can simplify it. Okay, so I'm going to simplify it, pull it out. This part can be pulled out here because it's the same in there and there, and end up with that. Okay, that was not easy to follow, and as I said, the examiners are not going to expect you to do this bit yourself. It's more likely that they might just ask you one quick question, okay, on something like part of the process. Points of inflection are where the second derivative is equal to 0. Okay, now then, from this, what we can see is part of it, this part here, for example, that if this equals 0, there's no way this part here could equal 0. Okay, it can't equal 0. It can't equal 0 because that part there is an exponential function. The exponentials can't equal 0. So that means that for the whole thing to equal 0, it's this bit here that must equal 0. Okay, that boils down to a little bit of an easier question, really, or an easier equation. What can I do now? Maybe bring this across there, times by sigma squared. So I put the 1 over, or taking that over really. Brought over the sigma, squared both tops and bottoms, which is where the plus and minus comes from. And then, just a little bit of arranging, took them over, and then I've got x is the mean plus or minus sigma. So all that really quite difficult calculus has boiled down to this one fact just here. And it's proved where the points of intersection are. The points of intersection, points of inflection, the points of inflection on any normal distribution curve, I've proved it to you there, are plus or minus 1 standard deviation from the mean. So that point there and that point there are the points of inflection on the curve. That's where your convex changes to your concave, and then your concave changes back to a convex. Okay. Right, one other little bit of maths before we move off normal distribution is you've done binomial distribution in the first year, so you know that binomial has a mean of 8, a number of trials which is 8, and a probability of 0.2. So out of 8 trials, the probability of success is 0.2. If I look at that as a table, this is what the probabilities would look like. What's the probability that out of the 8, no successes? Relatively small. What's the probability of getting out of 8, 1 success? That's the highest one. Okay. What's the probability of getting 2 successes? Because the chances of me getting a success is about 0.2. That's quite high as well. And then 3 successes, a bit smaller. 4 successes, very unlikely. 5 successes, really unlikely. And 6, 7, and 8 are hardly visible. Okay, so that's how you plot or show the probability distribution on a graph for a binomial. If I increase that value from 8 to 20, look at the difference in the graph. The difference in the graph looks like that. Okay, chance of getting 0 out of 20 is very small. 2 out of 20, or 1 out of 20, sorry, is getting big. 2 out of 20 is getting even bigger. Most of the results are roughly about 4, which makes sense. 20 times 0.2 is about 4, that's the average. And then it starts to decrease again. But look at the difference between those two, then all you've increased is the trials. Right, if I tried 50 with 0.2, look at the graph I get there. And that graph, you should be looking and thinking, I recognise that graph. It goes up to the mean in the middle and then comes back down. And that's only 50 trials. Okay, that's not very many. If you did 500, then you'd have a very smooth curve. Even though it's discrete, this is the difference, it's discrete data. Okay, you either have 1 success, 2 success, 3 success. You can never have 1.5 successes. So they're discrete bars with gaps in the middle. But what you're noticing is it's starting to get closer and closer to a normal distribution. The larger the number of trials, the closer that binomial distribution starts to approximate a normal distribution. It gets really close. Small number of trials is rubbish. Big number of trials is really, really good. Okay, right. Let's look at the opposite then. Let's look at the probability. So here we go. 20 trials, 0.1. Look at the graph of that. Okay, 0.1. Quite a lot. Nothing wrong with having quite a lot of failures because it's 0.1. If it's 1 success, that's very high. 2 successes is the norm. That's what you expect. 0.1 times 20 is 2. And then it starts going down. And there's no point in going past 6. It's just ridiculously small. Okay? Even though it might be, there's a probability of it happening. It's too small to worry about. And what about if we get that probability up a bit? We go to 0.5. Well, at 0.5, it looks like that. Okay? That's the same set of data, 20 trials. All that's changed from there to there is the probability of success. And look at that. When you're at 0.5, that's very good as an approximation for normal. It's got mean, 2 bars, like equally spaced out. It's very symmetrical because it's 0.5. That means it's a 50-50 chance of success. If you go further, 0.8 on the opposite end, it's not bad, but it's definitely not normal because you've got this sort of smoother curve here and then a big drop off down to 20. Okay, so although it's not bad, it's not as good as 0.5. So that combination, that's increased by 50 as well on there. But that combination of results changing means the closer you are to 0.5, the closer the binomial distribution approximates a normal distribution. That means we can just put some analysis into this. Don't need to do too much, just a bit of understanding that if we've got a binomial distribution, then and we want to do some approximation with it, you might need to if your end value is too big. Now in the past, now that calculators can handle it, it's not so important. But in the past, the end value was capped. You could only get a certain amount of end values. And the same with probabilities. You couldn't have a probability of, let's say, 0.17. The probabilities that were covered with it before calculators can manage it were very standard ones like 10%, 20%, things like that. So before calculators can handle it, it was important to be able to change to a normal distribution, because if you can change to a normal distribution, you can calculate it using the normal distribution tools. Okay, now the mean and the variance of the binomial distribution are worked out like this. The mean is n times p. We've seen that before, that's nothing new. And the variance was the number of trials times by the probability times by the probability of success times by the probability of failure. Okay, whereas the mean was the number of trials times by the probability of success. Right? Now, once you know both of those, that means that you can substitute those values into the normal distribution. You can see that's your mean, that can go in there. That's your variance, that can go in there. And then once you've got both of those in, you can then use your normal distribution model and part of the calculator to solve questions. The only way you could do it though is if the number of trials is large. It's a bit vague being large, but you've just seen a minute ago that 50 wasn't bad. The probability of success is close to half. So you could get away with having the less trials if your probability of success is really close to half. If it's not close to a half, if it's like 0.1, then you need lots of trials for it to be a close approximation. So the word large is very much dependent on the probability. Close to 0.5, you can have a small amount of trials. away from 0.5, you need a bigger amount of trials. The approximation would still be appropriate if both the NP and the n times 1 minus p are both greater than 5. That's a nice little tool just to use. If the approximation, to use approximation, if you try the mean and it's greater than 5, that's good. But also, if you try the number of trials times the probability of failure, okay? It's neither of these two things, but it's a good indicator to whether the approximation is still good. And the examiner will expect you to know that. They could ask you that. Is this appropriate? You can say yes, because the mean is above 5, but also the number of trials times the probability of failure is greater than 5 as well. But nowadays, as I said earlier on, modern calculators make the whole process unnecessary. So the only thing that an examiner might ask you to do is either a bit of converting like this, or more likely ask you a question about it like this. Is it appropriate to use with a normal distribution approximation? Right, what I'd like to do is just have a quick go on exercise 2.2. It's not a very big exercise. It just allows you to do some converting between binomial and normal.